So welcome everybody to this Friday seminar of ICS. Originally, we had planned Marcia Parisi to be here from California, but she had visa issues. So I'm very happy that Anders Johansen was jumping in, and he's giving the ICS seminar today. And just a few notes up front about Anders Johansen. So he is a professor both in Lund and in Copenhagen. So he is a professor of astronomy at the Lund Observatory, and where he works on planet formation, accretion disks, and supercomputing. And then he also holds a position as a professor at the Planetary Sciences and Planet Formation at the Globe Institute at the University of Copenhagen. So this is his main time investment as a professor. He obtained a PhD in 2007 at the Max Planck Institute for Astronomy in Heidelberg. After this, he did a postdoc at Leiden Observatory, and later on he went to Lund, where he received his docent degree in 2013. So his research is quite widely spread. It mainly focuses on theoretical and computational models of planet formation. So he cares about how to grow pebbles, how these are accreted to form planets and eventually entire planetary systems. And with this introduction, I will hand over to Anders. Anders, the screen is yours.
Okay, thank you very much, Caroline, and thank you very much for this invitation. I'm happy to be here virtually. Of course, it would have been nicer to be there physically. I visited the department a number of times and given seminars, and it was always very nice to be there. But maybe next time I can visit physically. So as Caroline said, my interests are mainly in planet formation, and one of the things I want to talk about today is actually an extension of my work on theoretical planet formation towards understanding the differentiation of planets, terrestrial planets, and also the outgassing of their first atmospheres. So I hope that I can excite you about making links between planet formation and sort of the geochemistry of differentiation and outgassing. All right. But the story of planet formation starts in these structures here, which are called protoplanetal disks, and they exist around basically all young stars that we can observe in the universe today. So planets form in such disks. They consist of 99% gas and 1% dust and ice. And what we're seeing here is actually, so these are observations done with the ALMA telescopes in Chile. And what we're seeing here are observations at millimeter wavelengths. Therefore, we don't see the emission from the star very much, but we see the thermal emission from the cold dust that is surrounding these disks, the cold pebbles of millimeter sizes. The disks are typical sizes of 100 astronomical units, so sort of similar to our own solar system. So that's telling you something about this, probably also the way our own solar system formed. And they have typical disk masses between 1% and 10% of the mass of the central star. But the last statement one can actually quantify as a function of time, because one can measure for star-forming regions that have different ages, and one can measure what is the fraction of disks that have a certain mass. And the unit here on the x-axis is the dust mass in units of Earth masses, and it's logarithmic. So this is 1 Earth mass, this is 10, this is 100, this is 1,000 Earth masses. And this plot shows the cumulative distribution of masses for class 0, class 1, and class 2 disks. And these disks are roughly starting class 0 and 1 are maybe less than 1 million years old, and class 2s are maybe a few million years old, up to 5 million years old when the disks finally vanish. And the reason that the mass going down with time is that gas and dust in the disk is simply accreted onto the star. Of course, there's a little bit going into planet formation also, but that's not the main part. Well, if you start early on in the class 0 phase, then the median value here is around 250 Earth masses of solid. That's a lot. Then we can see at the class 1 phase, after approximately 1 million years, maybe we're down at 100 Earth masses. Then we can see after a few million years, we're down at a handful of Earth masses, or a couple of handfuls of Earth masses. So the dust mass falls to 10 Earth masses after a few million years. What we learn from this is that the protoplanetary disk live only for a few million years. And that must mean when we want to form planets out of this dust and the gas in the disk, then we must do it rapidly, so within a few million years before the gas and before the disk is emptied onto the star. Okay, so planet formation is a race against time. Now, the first step of planet formation is actually relatively fast. That is the growth from micrometer-sized dust particles to 4 millimeter-sized pebbles. And this is what we call dust coagulation. I'm showing here a global calculation that my PhD student Lene Eriksson led in this paper from 2020. And this shows as a function of the distance from the star here in a model between 8 and several hundred AU, it shows the particle size in meters. Just look at the top plot here. These particles all started out being micrometer in size, but the protoplanetal disk is so dense that the particles collide very often. And this means that there's a very, very rapid growth. So you see the blue dots are 50,000 years, so after 50,000 years, we form millimeter-sized pebbles all the way out to 50 AU or so. There's still a bit of growth left behind here, further out, but as we increase time to 200,000 years, 350,000 years, we can see that basically we turn the whole disk inside of 100 AU into millimeter-sized pebbles. So this is a very short time scale compared to the millions of years of lifetime of the protoplanetary disk. Why don't they grow any further, these pebbles? That's because the further growth is hampered by fragmentation and bouncing. When these millimeter-sized pebbles collide with each other, then they don't stick so well anymore. There's also another problem here, that is that the pebbles drift towards the star due to friction with the gas. And that means that we cannot continue to form planets just by dust coagulation. We have to do something else now. And that something else is gravity. We need to have a lot of pebbles coming together in dense clumps so that they can contract under their mutual gravity to form planetesimals, which are like asteroids in the asteroid belt. And of course, the gravitational attraction between two pebbles is tiny, so we need to have a lot of pebbles coming together somehow. Now, a lot of mechanisms have been proposed to get pebbles together and concentrate in the gas. I'm going to talk today only about the so-called streaming instability, something that I work on a lot, and which is a very efficient process of turning pebbles into planetesimals. And the way that the streaming instability works is that we start with micrometer-sized dust grains as before. We coagulate them to form millimeter-sized pebbles. These pebbles are actually, it's a picture of pebbles made in a lab in Braunschweig. They're actually aggregates made out of micrometer-sized pebbles. So the grid here is 1 millimeter. But it's sort of, if you take such a pebble between two fingers, you can crush it with the slightest force, basically. So such pebbles don't stick when they collide. But now we have the streaming instability, which I'm illustrating here. And it works in the following way, that if I have an isolated pebble here orbiting around the star, then it will feel a headwind from the slower moving gas. The gas is moving a little bit slower than the Keplerian speed, because the gas is feeling two forces. One is the gravity that will make it orbit at the Keplerian speed. There's also a slight force pushing the gas outwards because the disk is hotter and denser close to the star and colder and less dense further away from the star. So there's a pressure gradient force pointing away from the gravity. And that means that effectively the gas feels a little bit of a weaker gravity, and therefore orbits a bit slower. That's these arrows here that are pointing down. Yes, and that acts like a headwind on the pebble, and the pebble will spiral in towards the star. But the streaming instability works in the following way, that if a denser filament of pebbles can form somewhere, then these pebbles can locally push on the gas and force the gas to orbit closer to the Keplerian speed. That means that the headwind becomes less. That's why they have a shorter arrow here. When the headwind becomes less, then the radial drift speed becomes less. And then you can see that this is now a runaway process, whereby the filament moves more slowly towards the star, but it keeps on getting fed by faster moving pebbles from outside. And this way the filament gains more and more mass. So that's the essence of the streaming instability, which was discovered by Yudin and Goodman in 2005, and which I then worked a lot on during my PhD thesis. This is what a computer simulation looks like for the streaming instability. The filament has formed, you see it here. It's like a 3D simulation, we're just seeing it in 2D now. And we see because of the gravity between the pebbles, the filament contracts even more to make these thin filaments here. And out of that condenses out planetesimals here, like a string of planetesimals here that have a range of sizes. The most mass lands in 100 kilometer-sized planetesimals, like this one here, like a typical asteroid in the asteroid belt. But some ends up in smaller planetesimals, like this little tiny dot here, which is like a 10 kilometer-sized comet. And actually also lots of the mass ends up in binary asteroids. So if I can zoom in, Actually, if you look very carefully here, these two are actually orbiting around each other. That's very cute. It happens when you go to higher and higher resolution, we form more and more binary asteroids. This is nice because it's very similar to those that observed in the Kuiper belt beyond Neptune, that there are many binary asteroids there. So we think that's another fingerprint of the streaming instability. There's also the contact binary Arrow-Cross, which was visited by the New Horizons spacecraft in early 2019. And that object was likely also formed by the streaming instability. This has been concluded in several papers. So that's a lot of evidence from the solar system that planetesimals probably formed by the streaming instability. Okay, but we want to go on from asteroids, and we want to form something larger. In order to know our starting point for planet formation, then we need to know the initial mass function of planetesimals. We need to measure how many planetesimals are there of each mass and each size. So as I said, the characteristic size of planetesimals formed by the streaming instability is about 100 kilometers. But if you have very big simulations with a high resolution, you can actually put a lot of dots on an IMF plot here, where we have the mass here in some dimensionless units, and here we have it in grams, and here we have the cumulative number, so how many are larger than a certain size, and these are the crosses here. And then you can try to fit various mass functions to that. And it turns out likely that the best fits are mass functions that go something like the NDM. That's the differential number of planetesimals in a mass spin between m and m plus dm. It goes as m to minus alpha, so that's a power law. That's what we see a little bit of here. When we go to low masses, we see sort of a power law. It's much more clear here in a paper from Simon et al. 2016. This is actually the differential distribution, and you see for different combinations of particle size here and metallicity, you can see that you can fit a power law to all of these curves here, and it looks something like m to minus 1.6. So that's sort of a power law here. But that one cannot continue to larger and larger sizes because it contains most of the mass in the large sizes, so it has to be cut off somewhere. That's why it has some kind of exponential cutoff here, x minus m over mx to a power law beta. And that's what we tried to calculate in this paper here from 2017, and we found this beta parameter to be quite shallow, like this between 0.3 and 0.4. So it's like a power law with then a very shallow exponential tapering on it. And this implies actually that there will be most planetesimals will be 100 kilometers. There will be a few lucky ones that may be up to 1,000 kilometers in size, so 1,000 times more massive than the 100 kilometers. Yeah. Okay. Now, in classical planet formation, then these planetesimals formed somehow will collide together, and then they will form the planets of the solar system and also the exoplanets. And one of the big challenges is to form actually the solar system, because here we have a plot where I show the distance from the star here in AU, and here we have the mass and Earth masses, and here you see Jupiter at 300, Saturn at 100, and then Uranus and Neptune here are around 20 Earth masses, all four. If you then let these planetesimals from this kind of size distribution collide together and grow, while also the planets are migrating towards the star, then you realize actually that it's very, very hard. So here this is a model here that I did together with Bertram Bitch, which is actually now accepted also and printed, where we then try to make Jupiter. So we start at 5 AU. We consider planetesimals accreting onto a beginning core, and what happens is that as Jupiter is then growing, and we put 1,000 Earth masses into the disk, which is of solids into the disk, which is a lot, then Jupiter is also migrating, and we can sort of form a hot Jupiter in the end. Which there are many of these in the exoplanet sample. So maybe this is just a way to form a hot Jupiter. But because the planet is migrating towards the star while it's growing, then maybe we should start further out. We should start out at 10 AU. But here the growth rate by planetesimal accretion is so low that basically we don't go beyond one Earth mass or something. So we don't really get to form Jupiter. And if you go further out to 15 or 20 AU, it gets completely hopeless. Nothing really grows. So it's really problematic to explain why Uranus and Neptune can have the masses that they have. We try with smaller planetesimals. So the blue line is the standard 50 kilometers. The red line are 5 kilometers. That helps a little bit that they are smaller. We can also take some different parameters and reduce the migration, for example. That's the yellow line. We're reducing the migration a little bit, but nothing really helps. It's a really, really big issue to form Jupiter by planetesimal accretion. So I should maybe have said here that Jupiter is 300 Earth masses, but of course it has a core of 10 Earth masses, which then accretes a lot of gas afterwards. So we want to go up to these 10 Earth masses. We can sort of do it, and that's what this plot shows. It sort of shows the final position and the final mass here. And we have Jupiter here at 5 AU and at 300 Earth masses. And you can see we can sort of do it if we go out and go to these dashed lines here, which has something to do with both having that the planetesimal midplane layer is not stirred so much by the gas, so that gives you a higher growth rate. And also with smaller planetesimals, we can sort of tweak it a lot, so we can just barely form Jupiter. But we still need to have 1,000 Earth masses to form just one Jupiter. That's very inefficient. And actually, this was done in sort of a statistical approach, zero-dimensional statistical approach. So there are n-body results basically showing the same. Thomas et al., Levison et al., Coleman and Nelson basically show the same problem with full n-body. Okay. And that's why we need Pebble accretion. So Pebble accretion is a mechanism whereby the pebbles that are over from the planetesimal formation stage, they can actually continue to drive the growth of the largest asteroids. And why is it more efficient to accrete a pebble than a planetesimal? And this is illustrated in this plot here. It shows a protoplanet which is growing, and it's now attracting a pebble here and a planetesimal here. And that protoplanet has a certain scattering radius within which it can scatter these objects as they come by. But scattering doesn't imply accretion. Typically, the planetesimal is just scattered and goes on a different orbit, a more eccentric orbit that makes it harder to accrete next time. Whereas the pebbles are accreted much more efficiently. That's because the pebble loses energy to gas friction. So as the pebble and the planetesimal are both out here, then they have an overall positive energy relative to the planet. They have positive kinetic energy. That's why the planetesimal doesn't get captured, right? But as the pebble moves through the gas, it loses energy by friction to the gas. And that causes the pebble to become gravitationally bound to the protoplanet. And then it has no choice but to spiral in and become accreted by the protoplanet. Yeah. And therefore, pebble accretion is much more efficient than planetesimal accretion is. So pebbles are accreted much faster due to energy dissipation by gas friction. Then we can sort of redo the experiment that I did before. Remember that I want to form Jupiter and Saturn, and then we can, for example, start out here in the 20 to 30 AU region. I mark it here as CO. This is the region where the CO molecule becomes ice. So this is a good place to start. Then you can see here that I can form, I can start at different times. This is early, and then I can start later and later. If I start early, I can very quickly build up a core of 10 Earth masses out there. Then it can start to accrete gas, and it can migrate in this region here that's sort of in the Jupiter-Saturn region. So because Pebble accretion is so efficient far from the star, then there's much more room to migrate over. Therefore, you can form Jupiter and Saturn by Pebble accretion. You can also go into the inner parts of the solar system. You can take the water ice line. It starts sort of at 3 AU and then it moves in. And if you start very early there, you can actually form Jupiter mass core, 10 Earth mass core, and grow up to Jupiter mass in gas. But then it migrates all the way in to become a hot Jupiter. So this is maybe a way to form a hot Jupiter. And if you start a little bit later, then the cores only grow to a few Earth masses, and they're not able to accrete gas, and they become more like something like mini Neptunes or super Earth. But the point about this is that because Pebble accretion is so fast, it can start further out, and therefore planetary growth by Pebble accretion can actually outperform the migration. And we can make planetary systems that are in full agreement with migration, which is good. Okay, I just wanted to show you some surprising piece of evidence maybe that Jupiter actually formed far from the sun and then migrated in. And that actually comes from the study of Jupiter's Trojan satellites. Let me just see if I can zoom in. So this is a map of the asteroids in the solar system, and I don't want you to look at the main asteroid belt now. I want you to look at these two populations, the Trojans and the Greeks. These are two populations that are trapped in stable Lagrange points orbiting together with the Jupiter. The surprising thing is that the leading Trojan swarm, the one called the Trojans, is 1.6 times more populated than the trailing swarm. So there's 1.6 times more bodies here than there are there. And this is actually unexplained. There's no reason why Jupiter would capture more. in front than behind it. So together with my PhD student Simone Pirani, we decided to explore whether Jupiter's migration would have been something to do with that. So basically we ran a bunch of simulations where we started Jupiter from anywhere from 7 AU all the way out to 32 AU. And then we put it into an n-body simulation. And in this n-body simulation, you can see here that we have Jupiter, Saturn, Uranus, Neptune. We have planetesimals everywhere, like test particles. We give them a color according to where they are. And then we make Jupiter grow and migrate. It's formed by Pebble accretion, so it grows fast and it migrates in. And you see the planetesimals are scattered all over the place. And then in the end, we are left with actually with some Trojans of Jupiter here. You see it has Trojans that it actually captured, so the blue color means that it captured the Trojans where it was a small core. So it captured the Trojans from the region where it was formed, actually. And the other planets also capture Trojans, but they are, Neptune's Trojans are stable, but Uranus and Saturn's Trojans are not stable, and they will be lost later. But the interesting thing is, if we then measure how many are there in front relative to how many are there in back, then we actually find that there's about this asymmetry factor of 1.6. We actually reproduce in all of the simulations that have significant migration. So you see here on top here, let me zoom in again. You see on top here how far Jupiter has migrated. So from 27 AU, we get a very nice asymmetry all the way down to 3 AU. We still get the asymmetry. But then when Jupiter only migrates 2 AU or 0 AU, then we don't get any asymmetry at all. And then Jupiter captures Trojans symmetrically in front and behind it. So how can we distinguish then? All we can say is that Jupiter migrates somewhere between 3 and 30 AU, could be even more. But then we think there's another evidence that Jupiter may be formed far from the sun. And that is if you look at Neptune's Trojans. So Neptune also has some Trojans. They actually look color-wise exactly the same as Jupiter's Trojans. And Neptune is now orbiting at 30 AU and was probably never really closer than 20 AU to the sun. So we think Neptune formed in the 20 to 30 AU region. And since Jupiter's Trojans have the same color as Neptune's, then we think that this might indicate that Jupiter formed in the same region as Neptune, which is basically what we're seeing here. That both Jupiter and Saturn and Neptune and Uranus form in this 22, 30 AU region. So this Trojan asymmetry is actually surprising evidence that Jupiter's core grew most of its mass far from the sun. Okay, now I want to move closer to the sun. And the Pebble accretion model was developed in order to explain the formation of giant planets, but I will argue also that Pebble accretion played a huge role in both forming super Earth and terrestrial planets that orbit closer to the sun. So there's a flux of pebbles going through the disk because of this radial drift, and this flux is actually very high. It can be, in the first millions of years, it can be maybe hundreds of Earth masses per mega year, and there's only a few Earth masses caught in the terrestrial planet zone. So obviously this is a lot of material that can grow terrestrial planet from. So in this paper from 2019, Michiel Lambrechts, who is a postdoc working with me, he was doing n-body simulations of the inner part of the solar system. And he included both the collisions between protoplanets and also Pebble accretion. So he starts a lot of protoplanets here between 0.5 and a few AU here. And then when he runs the simulation with a low Pebble flux, so maybe just a few 10 Earth masses per mega year, then you can see that these protoplanets are all growing, but not so much, maybe up to a few Earth masses, so sort of mass. They migrate a little bit, and then basically the game is over. After 3 million years, the disk stops. So then we can go over here and say this is where we are after 3 million years, and then when we wait for 100 million years, then we actually have classical terrestrial planet formation. These protoplanets are colliding with each other, and they sort of make a Mars and an Earth and a Venus here that is one Earth mass, and further out they make sort of a Mars that's point of view Earth mass. So that is classical terrestrial planet formation in a combination with Pebble accretion forming the original protoplanets. But if we increase the mass flux of the pebbles just by a factor of 5/30 up to maybe 50 Earth masses per mega year, then something else happens. The protoplanets are growing and very, very efficiently. They start to migrate a lot. They start to collide with each other. That's why some of these lines end here. And we end with a population of super Earth, basically between 2 and 10 Earth masses, just by changing the Pebble flux a little bit. And we see after 3 million years, we have sort of these super Earth systems that have many, many bodies in them. But actually the bodies are so close to each other that they will collide in like hypergiant impacts. And then you end up with systems that are sort of with a characteristic mass around 5 to 10 Earth masses. You see the characteristic mass going a little bit up from here to here, okay? So this way, the formation of super Earth and terrestrial planets are actually connected processes. It depends on the availability of pebbles. Many pebbles available, super Earth, less pebbles available than terrestrial planets. And yeah, I guess I don't want to talk about this plot too much. I just want to say that they are typically in resonances here. The super Earths, they are in orbital resonances, which we don't observe too much in the data. But actually, when you go from this stage to this stage after the giant impacts, then these resonances are broken, and then it starts to look a lot more like what we observe. Okay, but we can take this one step further, and then we can say, hey, we could almost form terrestrial planets here. So here are our embryos, here are super Earth. What if we could actually form terrestrial planets by Pebble accretion alone? And we can. Now, these are not in-body simulations. We are back in the sort of single planet simulations again. But one thing that I found intriguing is that if you look at Venus and Earth and Mars, then they sort of look a little bit like a Pebble accretion growth track. There's a small Mars and a larger Earth and a larger Venus. And that's because the larger you are, the more you migrate. So the larger planet should be on the inside, and the smaller should be on the outside. And if you try to run a Pebble accretion model, then for a realistic protoplanetary disk, with realistic particle sizes, from planetesimal starting around 1.6 AU, then you get these black lines here, and you actually see indeed that these three planets are sort of following along the growth track of Pebble accretion, which I think is really intriguing. Of course, some of you with sharp eyes will have noticed that the Earth doesn't fit too well. The Earth should have been less massive than Venus, and Earth is actually, in fact, more massive than Venus. But of course, Earth needs to have a giant impact. Because of the moon, Earth-Moon formed in a giant impact. So that Earth must have been smaller originally and then collided with another planet. This planet is typically called Theia, and we placed it here in the solar system at 0.4 Earth masses, Earth at 0.6 Earth masses, and then we say that later on Theia will collide with Earth, proto-Earth, and then it's going to make Earth. This is in a way nice because when Theia and Earth form out of the same drifting material, then they also get the same composition. In terms of isotopic composition. And this can then explain actually why the Earth and the Moon have so similar isotopic composition. It is because the moon forming impactor had almost the same composition as the proto-Earth had. So this way planetary migration shaped maybe the masses and orbits of giant planets and also terrestrial planets. This is showing the mass growth about the time. We start them at different times. Venus, Earth early, then Venus early, then Theia a little bit later, and then Mars a little bit later. You can see that the contribution from planetesimal accretion is the red line. Now we are in the inner part of the solar system, so planetesimals are accreted much more efficiently. And you can see, for example, Mars has almost 50% of its mass from planetesimal accretion, whereas Venus and Earth and so on stop around 0.1 Earth masses with planetesimal accretion, and then they accrete the rest of the mass mainly by Pebble accretion. We can also vary the parameters a little bit. This was obviously here we was taking the optimal parameters, but instead we can say, well, let's just see how we can vary the parameters. We can now start planetesimals around 1.5 AU, and then we can let them grow at different times. Then we get these black lines here. This is populations of planets that are formed by a Monte Carlo method. And we can see here that we can see that Mars, Earth, and Venus are actually very characteristic of this growth track, even when we do a Monte Carlo modeling around it. If we don't have a thin planetesimal belt around 1.6 AU, but we have planetesimals spread all the way from 0.5 to 2 AU, those are the green dots here, then you can see that we no longer have a characteristic planet size. In this, we have planets that have masses all over the place, and so therefore the terrestrial planets are more consistent with forming out of a thin region around 1.6 AU. We can also vary the metallicity or the pebble flux. Here is a pretty low pebble flux, maybe a few 10 Earth masses per mega year. We can increase it, and indeed we get a higher mass. Then you see that the black dots are now above Earth and Venus, and also the green dots are more or less approaching super Earth again. So again, here we are showing that it's the pebble flux that determines whether you're going to form super Earth or whether you're going to form terrestrial planets. Okay, now comes sort of the second part of my talk, where first I've shown you now that there's a different way of forming terrestrial planets than we normally think, because terrestrial planets could very well form by Pebble accretion. But then we wanted to explore also what are the implications about this for the differentiation for the Earth and for other things. So we want to address some of the open questions in terrestrial planet formation with pebbles, like how are volatiles such as water in the accreted pebble thermally processed in the planetary envelope? How do terrestrial planets differentiate if you don't have giant impacts? Normally we assume that it's giant impacts that make magma oceans and differentiate them. Can we reconcile the rapid accretion of terrestrial planets with the low excess of radiogenic 182 tungsten over 184 tungsten for Earth. I will explain later what that means for those of you who are not intimate with that cosmochemical system. And are the abundances of volatiles delivered by pebbles consistent with the compositions of Venus, Earth, and Mars? Yeah, and we have 3 papers now that are submitted to Astronomy and Astrophysics where we address these questions. Still waiting for the referee report. All right, let's start with volatile delivery by pebble snow, because pebbles deliver volatiles in a very different way from giant impacts. So I have sort of a sketch here actually that my wife made for me of what it looks like when a planet is going by pebble accretion. So in here we have the core and we have the mantle, which is turning into a magma ocean. I will show that in the next slide why that is. There's an outgassed atmosphere, which I'll also come back to. And now we are with 1 Earth radius approximately. But beyond that, all the way out to the hill radius, there's first a convective bound envelope of gas accreted from the protoplanetary disk up to 100 Earth radii. And then up to 1,000 Earth radii, there's what I call the recycled envelope. The recycled envelope can be illustrated here. This is a hydro simulation of a planet disk, of a planet embedded in a protoplanetary disk. Here, the planet is in the middle somewhere. This shows the density, so you see that it's accreted some kind of gas envelope. But notice that the outer part of the hill radius, there are flows coming from the hill sphere from the protoplanetary disk into the hill sphere and then out again. These flows are what I call recycling flows because they can bring material released inside the hill sphere. They can actually bring it out again, and that's what I'm showing here also. That in this region with the recycling region, if so here I put the temperature out at the protoplanetary disk to be so low that water is basically ice. But you see at some point the temperature becomes 170 Kelvin and the ice starts to sublimate off. And if it does so in this recycled envelope, then all this water vapor will be transported back to the protoplanetary disk. Yeah? So this way the pebbles get thermally processed on the way down and they lose all of their water out in the recycling zone, and that gets sent back to the protoplanetary disk. Okay, and that means that if we then calculate as a function of the mass of a growing planet, what is the water fraction? Let's just look at the blue line here. It starts out being low. You start as a dry planetesimal, then you accrete a lot of ice. You're outside the water ice line. The pebbles contain 30% ice. So you would have been a water planet now with 30% water. But as you reach 0.01 Earth masses approximately, then the temperature in the envelope becomes high enough to sublimate ice into water vapor. The water vapor gets recycled back to the protoplanetary disk, and then we don't accrete water anymore. And then the fraction falls and falls and falls all the way up to we end accreting here at 0.6 Earth masses. And we can see here 2 different models for the water. Here's 35% water and the pebbles. Here's 10%. You see that we end up with a few thousand ppm or a few. So this is 1%, this is 0.1%. So a few times 0.1% water. And these are the estimates of the water amount on Earth. These are these 2 dashed lines here. So this way we can sort of explain the amount of water on Earth that Earth formed outside of the water ice line could have accreted 30% water, but in the end, a lot of it just got transported back to the protoplanetary disk, and that's why actually the Earth has so little water. You could do the same game with carbon. Carbon sits mainly in organics in the pebbles, and this is both sublimated and pyrolyzed between 325 and 425 Kelvin. There's a bit of graphite that is refractory that burns at 1100 Kelvin, and then you can make a carbon line here where you also start so to say, accreting maybe a few thousand ppm of carbon. That's what the pebbles contain. But then after a while, the envelope gets so hot that the carbon is processed also, it goes back to the protoplanetary disk, and you end up with something like 500 ppm of carbon, which is very similar to the geochemical reservoirs on Earth. So this is what was called pebble snow by Ida et al. In 2019, and we show in this paper here that the pebble snow actually gives a good match to the water and carbon contents of the Earth. Yeah. Let's just contrast this now with the classical model, and that is that the Earth formed outer planetesimals that are colliding with the protoplanet. And the newest planetesimals we have in our solar system are the ones that are in the asteroid belt now. And there are meteorites for all those planetesimal classes. There are the ordinary chondrites that correspond to the S-type asteroids closer to the Earth. There are the instatype chondrites that correspond to the E-type asteroids, I guess, that are even closer to Earth. There are the carbonaceous chondrites that correspond to the C-type asteroids that are further away from Earth. But there is a problem with all of those. And that is, if you look at their nitrogen contents, this is nitrogen over silicon here, you see that all of these reservoirs here have way more nitrogen than the Earth has. Yeah, and that's actually a problem because the Earth contains only 1 to 3 ppm of nitrogen in this atmosphere mantle. Venus contains almost the same, so that's sort of an indication that this Pebble accretion model may be correct, that it's not random how much you get, but you get it down with the pebbles. But then people are aware of this problem and they will say, okay, the reason why the Earth has such low nitrogen is actually that they are accreted from these bodies, but a lot of the nitrogen will be in the core now. And that's certainly a possibility. So that's what we call siderophile, that the nitrogen likes to go into the metal core. But the problem is also that nitrogen is also what we can call atmophile, that nitrogen doesn't like to be dissolved in the magma ocean. It tends to gas out as an atmosphere. So there's a competition between nitrogen in the magma ocean, what goes into the core and what goes out in the atmosphere. It actually turns out that the atmosphere wins, so it's very hard to store in the core. And I can show you the plot here, where we did some experiments, basically, where we say, okay, but depending on the partition coefficient of nitrogen between metal and silicates, this is 1, so it will be equal concentration in metal and silicates. 10 means there's 10 times more in the metal than in the silicates, and 100 is 100 times more. And we can see how much of the fraction of nitrogen that we accrete with the pebbles actually ends up in the atmosphere. It's nearly 100% for a partition coefficient of 1. And then even for 100, it only goes down to something like 50%. And you see the amount that's in the core starts out at being only 1%, and we can sort of bring it up to 50%, but we cannot bring it up to the 99%, which would be needed to store nitrogen in the core. However, if we run our Pebble accretion model now, we can include nitrogen. So I showed you before carbon. Our carbon is initially at a few thousand ppm. This is now ppm. Then it starts to go down as the organic molecules are destroyed and the carbon turns into CO and CO2, which are vanishing. The same happens to nitrogen. So the nitrogen sits mainly in the organics. The organics are destroyed with higher temperature. The nitrogen turns into N2 and NO2 and other molecules that are very volatile. And they also escape back into the protoplanetary disk. So we can start at something like 10 ppm, that's sort of the ordinary chondrites here, and then we can take this into pebble form. We can process these pebbles in the envelope of the planet, and then we can actually reduce it to a few ppm. So this way, we think that that the low abundance of nitrogen, and also the same goes for noble gases on Earth, could be the smoking gun that terrestrial planets formed by Pebble accretion and not by accreting planetesimals that are similar to the asteroids in the asteroid belt. All right. How long do I have, Caroline? Sort of.
You have 5 more minutes, but you can also have 8 more minutes. So it's like
okay. Yeah, I think
flexible.
Okay, yeah. I think I might just skip the one part here. Then I'm going to go directly to here. So I talked about the magma ocean, but I didn't really show you yet how to form a magma ocean. So as I said, in classical terrestrial planet formation, when there are giant impacts, then the whole mantle melts and it forms a magma ocean that would then differentiate so that you get a core and a mantle out of it. But with Pebble accretion, we don't really have so many giant impacts, but we have a lot of accretion energy still. So let's just start with this plot here. This shows our Earth forming, and you see as a function of time, Earth accretes up to 5 megayears, and then it stops accreting. And on the right axis here, I have the surface temperature. That's actually the blue line, that's the surface temperature, and the yellow line is the photosphere temperature, so the effective temperature. Let's go here. 0.1 megayears, this is what the planet looks like. We are down here very, very early on. It's only very, very low mass planet. And basically it only has enough accretion energy here to so that the water is melted, so it came from ice to water. Some of the water will form a clay form in the center, so it's like a clay ball, and then it has a water ocean on the top here. Then we can go forward in time. We go to 1 megayear. We're still very cold. The accretion energy is not very strong yet. Then we are differentiating now into a core and a mantle, and that's because there's a radioactive decay of aluminum-26 in there. Which is also what is responsible for differentiating asteroids. So that's an early core that forms here. But then after 3 million years, there's not so much aluminum-26 left, and we keep on again only heating enough to actually melt ice to form water and to form clay here. See, this is at 3 million years, and the effective temperature is still only 100 Kelvin, 200, 250 Kelvin or so. But then as the planet grows larger, then it has so much accretion energy because now there's a deep gravitational potential that the effective temperature goes up to something like 300 Kelvin or a little bit more. And now it's starting to sound like Venus, right? Venus has such a solar insolation that basically triggers a runaway greenhouse effect. And that's what happens here also. At some point, there's a runaway greenhouse effect where the water in the oceans here are getting vaporized into the atmosphere, and that causes a greenhouse effect that heats the surface, that takes more water into the atmosphere, and this way the whole water ocean is basically lost here and goes into a thick atmosphere, and the surface temperature you see here goes up then to a few thousand Kelvin, and when it goes up to a few thousand Kelvin, then the mantle basically melts, and let me see, and the planet differentiates from the surface and down, so the energy released by the falling metal, then metal and silica separate, the metal falls down, and that heats even more by releasing gravitational energy. And then you actually get sort of a runaway differentiation of the body into a massive core and a massive mantle. So that results in a fully molten magma ocean. Yeah. Okay. Now, in this model here, Earth formed very quickly within 5 million years, and we've got to look at whether there's some evidence from our own Earth that it could have formed that quickly. And normally people would say that the Earth formed in maybe 30, 40 million years, and the reason is the following: that is the so-called hafnium tungsten system for Earth, what you can use to date core formation. And the system is such that 182 hafnium decays to 182 tungsten with a half-life of 9 megayears. And then tungsten enters the core. It likes to go with the metal and go into the core when you differentiate, while hafnium likes to go with the silicates and it remains in the mantle. So when you remove all the tungsten from the mantle and you differentiate early, then there will still be hafnium 182 left that will keep on producing 182 tungsten, and then the mantle will suddenly contain a lot of 182 tungsten, because that was all created by hafnium, while the 184 tungsten that you normalize it by is all now in the core. So the mantle excess of 182 tungsten can actually reflect the time of core formation. Let me show you our model here. We form Earth in 5 million years, up to 0.6 Earth masses, and then we wait 40 million years, and then we make a giant impact with Theia that makes the Earth 1 Earth mass. And you can see what happens here. You measure the excess of 182 tungsten by some means, just by some quantity called epsilon W, and I don't really want to tell you much about what that is, except that it's 0 for Earth by definition. And you can see when Earth forms its core so quickly, look at the red line here, then Earth builds up an enormous excess of 182 tungsten, which we don't observe at all. It should be 0, and now you see it goes up to 10. So that's completely wrong, obviously. But then luckily we have the moon forming giant impact. So the moon forming giant impact, when Theia smashes into Earth, Theia's core is filled with tungsten, which is nice. So this tungsten comes now out into the mantle, and it then makes the 182 tungsten excess far less, since there's a lot of 184 tungsten in the core of Theia. And then bam, you're bringing the excess of tungsten down to -1. Then there's still a little bit of decay in tungsten of hafnium into tungsten in the next 50 million years, but then it ends up here at a nice 0. So the moon forming impact can reduce to epsilon W equals 0, as we observe, if the impact is massive. So therefore, rapid Earth formation is consistent with the hafnium tungsten system, and that was sort of implied also in papers by Yu and Jacobson from 2011. Okay, so we can actually map that out, and we can say what mass of Theia, the impact do we need, and what time of the giant impact do we need in order to reproduce Earth small excess of 182 tungsten. And we want to have 0 by definition here. And you can see that the 0 line here goes in a region here where the impact is at least 0.3 Earth masses, and where the time of the giant impact is at least after 35 megayears. That is, if we have 100% equilibration between the core of Theia and the mantle of Earth. If only 50% of the metal from Theia's core equilibrates with the mantle of Earth, then the 0 line moves here. We sort of need 2.5 Earth mass objects to collide with each other. So a planet accretion timescale of 5 megayears, as we have, that favors a massive impact at least 35 megayears after the start of the solar system. And this is actually nicely consistent with the necessity to have significant mixing in the moon forming impact. So we think this really works well if the impact is very massive. Okay, so I promised you a little bit about the outgassed atmosphere, and that's going to be my last 2 slides or so. And this is actually something that I think Caroline knows a lot more about than what I do, so she can correct me if I say something wrong here. Basically, when you have a magma ocean, it gets filled with volatiles from the pebbles, or from the planetesimal, in case of planetesimal accretion. When that magma ocean crystallizes after the end of accretion, then these volatiles come out. And what comes out depends on something called the oxygen fugacity. And the oxygen fugacity in geochemical terms is sort of the fraction of triply ionized iron versus doubly ionized iron in the magma ocean. So it has to do with whether the iron is bound with an oxygen, in which case it stays in the mantle, or whether iron is metallic and then it goes into the core. And then oxidized iron can come in these two forms. And I just want to show you first what happens if we just take the nominal model, which is sort of mass, our mass model, so 0.1 Earth masses, and it has basically an oxidation degree that's set by the amount of iron and the amount of oxygen that Mars accretes. What happens then is that, so after 5 million years here, Earth stops to accrete, and then the magma ocean crystallizes. It spews out all of the gas from the magma ocean. And you see most of this actually becomes H2. So H2 gets outgassed as H2. Now H2 is very easy to escape. So the early sun had a lot of very strong XUV radiation that would make this H2 to destroy it and make a wind of H2 escaping from the planet, and that would drag along with it everything else. It would drag along the water vapor. That's what you're seeing here. This is the water vapor in the atmosphere that also escapes, and it will also take along with it basically all of the CO2. That's what we see here. This is the CO2 for Mars, and also all of the CO. Everything just escapes away together with this H2 atmosphere. In the end, it's only when all the atmosphere escapes after 50 million years that Mars gets so cold that it can hold on to the rest of its water, and it gives something like somewhere between a 500-meter layer and a 1,000-meter layer of water on Mars. So that can maybe explain why Mars has so relatively little water. We think that Mars originally had maybe between 500 and 1,000 meters of the water. Okay. Now, it turns out that as a planet becomes more massive, so more massive than Mars, all the way as massive as Earth, then there can be chemical reactions going on in the bottom of the magma ocean that would turn Fe2+ into Fe3+. That's effectively oxidizing the mantle more and more, and that means that the mantle will be more willing to outgas H2O and CO2 instead of H2 and H2O for Mars. So when we take our Earth model, which is far more oxidized, then we see we get almost no hydrogen out, just a little bit in the beginning here. Most of the mass comes out in water vapor instead of H2, so oxidized H2 that cannot drive this massive outflow luckily, so Earth can hold on to its atmosphere. And that means that basically Earth very quickly cools down, and then it lands with an atmosphere, with a water ocean. It's about 1 Earth ocean. Yeah, that's good. We can also see that we start with we get actually a CO2 atmosphere outgas here, not so much CO, but mainly CO2. That's sort of similar to Venus's CO2 today. So we start with an early, very thick CO2 atmosphere. And we think that actually agrees kind of well with the idea that Earth and Venus initially had the same kind of atmospheres of CO2. Then Earth buried most of its CO2 atmosphere into the oceans afterwards. Yeah. Okay, so that was a difference. I wanted to show you this one here. That actually what I didn't show in the other plot was that a lot of the volatiles will go into the core also. And particularly water and carbon, they are actually solidifying. They prefer to be with metal melt rather than silicate melt. So the partitioning of water and carbon between mantle and core is a key process that determines the atmospheric composition. And the partition coefficient is the concentration of something in the metal versus that in the silicates. And if D is high, then there will be more material in the metal than in the silicate. We call it to be siderophile. Okay, these partition coefficients for water and for carbon depend on a lot of things. People have done nice experiments and measured them. But I just wanted to do here a little bit of a numerical study where we vary the partition coefficient of water between 1 and 8, and that of carbon between 1 and 10,000. Let's start with the water. So if we do 8, then the water prefers to be in the metal, and a lot of water will go into the core, right? And then you can see here, this is, by the way, the core is the red here, Earth is the circle, Mars is the star. When we have 8, then basically most of the water lies in the core. And we have something like 20 Earth oceans of the water actually lies at the core. And you see what's out on the surface, then in this case for Earth is less than an Earth ocean, half of an ocean. And for Mars, it's really, really little. It's like 0.01 Earth oceans or something. As we are reducing the partition coefficient of water, more of it goes into the mantle, then it can go into the atmosphere. And we see we get less and less in the core. It goes down, and we get more and more into the oceans. And at a value around 5, which is luckily what they found in this paper, Leader 2020, we get sort of 1,000 meters ocean on Mars and 1 Earth ocean on Earth, which is good. because it's reduced massively from the 20 Earth oceans that are actually accreted by the pebbles. Most of it would be in the core, and we get good agreements with Mars and with Earth. We could do the same thing again for the carbon. So this is the carbon. Carbon is much more acidified than water, probably really prefers to be in the metal melt. And then we can see if we have a very high partition coefficient, that basically most of the carbon is sitting in the core of Earth. The core of Mars is less massive, so then there can be less carbon. As we reduce the partition coefficient, we're losing all of the carbon from the core eventually, and we get it into the surface, into the atmosphere here of Earth, but not for Mars, because the hydrogen of Mars just blows it all away. Mars never has an atmosphere in these models. And we can see at a value of around 300, which is sort of the nominal value, we get sort of Venus's CO2 amount out into the early Earth, and we think that this makes sense because then Earth has oceans that can then bury the CO2 into the mantle later on. Okay, so what I wanted to conclude here is that this Pebble snow model, that gives actually a predictable amount of volatiles delivered to terrestrial planets. So you see Earth and Mars have the same water amount delivered. It's a little bit of difference in carbon to Earth and Mars because there's some of the carbon that comes into refractory form, but it's sort of within order unity the same. So they get the same volatiles, but then later on the mantle oxidation state, the core mantle partitioning, and also atmospheric loss leads to a diversity in the final volatile budgets, but in a predictable way. So we will predict always that a Mars mass planet would evolve like Mars and an Earth mass planet would evolve like Earth. And I think this is in a strong contrast to classical terrestrial planet formation by planetesimal accretion and volatile delivery by planetesimals, where it would be much more stochastic. Okay, coming to my summary, I talked about forming planetesimals by extreme instability, about 100 kilometers in size. There may be a minimum planetesimal size. I didn't really discuss that, but it may be that it's hard to make small planetesimals. The extreme instability makes prograde planetesimal binaries that increase with the contact binaries in the Kuiper belt. Pebble accretion is an efficient mechanism to grow the cores of gas giant planets, even if there's migration. I have shown you a new Pebble accretion model for Earth that allows our planets to form exterior of the water ice line in the solar protoplanetary disk. I showed you that Earth could form in 3 to 5 megayears, and this is consistent with the hafnium tungsten dating of core formation if you have a massive moon forming impact. And I showed you that the volatile deliveries of Venus, Earth, and Mars are consistent, I should say, are consistent with delivery by Pebble snow and inconsistent with chondritic building blocks. And with that, I will stop.
Thanks so much. Great talk. Thanks so much for all these details. Sorry, I wanted to have the clapping sign. That's great. I open, so the floor is open now for questions. And if you have a question, just raise your hand. I have noted down many questions, but yes, I see Judith has a question.
Thank you. Hi, Anders. This is Judith Sulaidi. It was a very nice talk. There were a lot of things in it, so I have a lot of questions, but I just start with one. Yeah. At the very beginning, you were talking about the size distribution and the initial mass distribution of the planetesimals, and all this is connected also your pebbles, no? And my question is how this initial size distribution evolves throughout the protoplanetary disk evolution, and maybe even in the debris disk phase, because that's important for terrestrial planet formation. And how does that included already in your models?
No, that's a really good question. So the IMF will be modified very strongly in the disk by collisions, right? That's also why the asteroid belt, anything below than 100 kilometers in size, is basically modified collisionally. Whereas if you go out to the outer solar system, collision timescales are far, far longer. So if you actually, where you want to go to find the original IMF is probably in the classical cold Kuiper belt. This is the outermost asteroid belt in the solar system. And if you go there, it does look a lot like a power law with an exponential. So it does look like this size distribution agrees well with the primordial size distribution in the solar system.
Okay, thank you.
Yeah.
So let's go to Paolo.
Yeah, thanks a lot for the presentation. I had a couple of questions. Maybe my first one was really more or less answered in that previous question, but I had another one regarding the water delivery. You showed that there's sort of a linear decrease in water concentration, or linear in log space, yeah. And I wonder, is this calculated based on the escape velocity of the planet, or do you just say that water is evaporated from the pebbles and is automatically lost thereafter, because you would imagine perhaps as the planet grows, the potential for it to keep the water increases as well. So
right. Okay, no. This is purely calculated from the position of the ice line in the envelope. When you're below 0.01 Earth masses, then the surface is still 120 Kelvin, 140 Kelvin. Then it starts forming this icy body early on, and then later on, I'm simply assuming that all of the water vapor is back into the protoplanetary disk. So I'm not assuming water vapor loss in the protoplanetary disk phase. What I'm trying to do now is actually, you can see in this drawing here that I said both an outgassed atmosphere that I showed you, there's also a convective envelope. And I sort of want to match these two at some point in the numerical simulations and try to understand a little bit also how mass could be lost from down here in the envelope phase. But sort of my assumption here is that the convective envelope is going to be at a lower entropy level, and it's going to be convective, but it's not going to be connected to the protoplanetary disk as it is here.
I see.
This down here is just kind of circling around. But we are running hydro simulations of this also, and I think it's a really important thing to explore more.
Okay, thank you very much.
I just have a follow-up question on this. So is the convective envelope, that's like the composition is like the protoplanetary disk gas, right?
Yes, it will be. It will be from the protoplanetary disk. What's going to happen, I think, if we are further out in the disk, then actually the ice line will not be sitting here, it will be sitting down here. Then if you're 20 AU, for example, then the water vapor will be released inside of the convective envelope, but then it's going to circulate around there. And the convective envelope is going to be a very high mean molecular weight. But I think that's more recipe to form Neptune, so to say, right? You need to be very cold in order to maintain in order to fill the convective envelope with the volatiles.
Yeah. Thanks. I see a question from Joachim.
Hello. Yeah, great talk. Thanks, Anders. I wanted to ask a question about what you showed as the initial planetesimal distribution at the beginning for the terrestrial planets. And it looked very uniform to me. And I was wondering, given that these things are forming in the streaming instability, why you do not have sort of rings or things like, concentrations of planetesimals in the initial distribution.
Yeah. Okay, so obviously we don't know where planetesimals formed in the early solar system. What I did here was to say, hey, 1.6 AU is a great place to start pebble accretion. Why would they form at 1.6 AU? But that could have been the early water ice line. So as you probably know, there are some models that form planetesimals at the water ice line. So what I did then was to assume that there were planetesimals forming mainly around 1.5, 1.6 AU in like a thin belt. And that also means that that's also sort of what you're seeing here, actually, that when Earth starts, let's take Earth would be this line here, it accretes almost 50-50 pebbles and planetesimals. But at some point, the planetesimal accretion levels off. And that's actually because the Earth is migrating out of this planetesimal belt. So a lot of this hinges on the, so whether you have classical terrestrial planet formation or pebble accretion terrestrial planet formation, it hinges a lot on the relative mass of planetesimals versus pebbles, right? And in this case, we're sort of driving it towards a little bit of a planetesimal start model, in which case the pebbles take over. But if we would have planetesimals everywhere, it would obviously be a different story. Yeah.
Judith, you have another question.
Yeah, just a follow-up for this one. How do you keep your pebble flux constant, or how do you, during the coagulation and during collisional cascade, how do you keep the pebbles? Yeah,
here I assume it's a relatively low flux. So I assume that Jupiter will be blocking some of the flux, maybe. So I assume that here that it's only 0.4% times the gas flux. So that is pretty low. And if it's higher, then you're going to form super Earth. So the only way to not form super Earth is that something has to reduce that pebble flux. That something might very well be Jupiter's formation, right? So that only a fraction of the pebbles make it through Jupiter's gap.
You have another question from Fabian Seidler. So I just read it from you for you. So he says, thank you. This was a really amazing talk and awesome work. Do you think that this model can be applied in a predictive way to exoplanetary systems and different initial disk chemistries?
Yeah, no, that's a really good question. I want to explore that more. But I think what I like about it is, of course, this idea that you can have basically for the same volatile budget, you can have different outcomes, but as I say, in a predictable way. right? So I think this would actually, what would I predict? I would predict that super Earth would not have more water than Earth. It would probably have about the same. I don't know, at some point it may be a problem to not have enough water because the surface is too large. On the other hand, super Earth could also form further out and migrate in. And if they form at such a place like what I said before, that the water ice line would be down in the convective envelope, then I think you would have something like mini Neptunes that would have a lot of water and a lot of rock and so on. But they would probably also create a lot of gas, and then I don't know how habitable that they would be. Another prediction I had, which I skipped for a bit of lack of time, is actually that I made this model here that shows the amount of FeO that would be so this is the core mass fraction as a function of the different planets. This is Venus, Earth, Theia, Mars, and Vesta here. And here I actually predict that as the planets grow larger, their core mass fraction becomes higher and higher, and also, and that's because the metal that doesn't go into the core, that's because it's become oxidized and stays in the mantle, and I only oxidize it by interaction with water, and I have the same amount of water for all planets. So super Earth also gets the same amount of water to oxidize iron with, and therefore it doesn't have a lot of ways to prevent metal from falling into the core. So I would also predict that super Earth would have higher core mass fractions.
I think our time is actually over, but so I will just say, like, for those of you who will stay, I don't know, do you have 5 more minutes?
Yeah, certainly.
Yeah. So I think, if those that want to stay, you're very welcome to. Otherwise, feel free to leave. Thanks a lot at this point already, Anders, for this seminar. This was very comprehensive and detailed. Thanks a lot.